then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students, and welcome to lesson number 7. Let's have at it. Okay, today's lesson is all about limit of composite functions. This is a very technical topic here. So this is probably our most technical topic thus far. We're really going to look at 3 cases. Each case is unique to itself. So you really want to pay attention on this. This was something that was really, limit of composite functions have been around forever. But this was something that was really emphasized in AP calculus just last year. And last year it developed quite a storm. So please pay close attention. This will be the most technical thing we have done thus far, but we should be able to handle it. So let's go ahead and look into limit of a composite function. So we're not going to review. Last lesson was over one-sided limits. When doing limit of composite functions, for certain cases, you have to utilize one-sided limits. So we can review one-sided limits as we're doing limit of composite functions. So let's look at our first case. All right, so this is case 1. And I want to read what it says very carefully to understand the case. So f and g are functions. L is a real number, of course. And it says such that f of x is continuous at x equals L. And if the limit as x goes to c of g of x is L, then the limit as x goes to c of f of g is f of L. I know that's a mouthful. Essentially what it's saying is this. Now, the first thing is that f of x has to be continuous at x equals L for this particular case. So you have a limit of a composite function, right? So you're encountering this problem right here. This is what you have to do. And so the first thing you do is you'll take the limit of the inside function. And so in this case, the limit of the inside function is L. So I take the limit of the inside function. I do it how I do regular limits. If f is continuous at x equals L, then the limit of the whole composite function is just f of L. That's pretty much it. So, and for all our cases, the first thing you're going to do is you're going to take the limit of the inside function. And if the limit of the inside function doesn't exist, then the limit of the composite function doesn't exist. But if you take the limit of the inside function and that number you get, if the outside function is continuous at that number, then you just plug that number into the outside function. It's kind of why we went over continuity in one-sided limits previously. So let's look at an example. Let's look at an example of case 1. Okay, so here's the first example. This is an example of case 1. So let's look at it. So here on the left, we have the graph of f of x. Here on the right, we have the graph of g of x. And it's asking us to find the limit as x goes to 1 of f of g. So in this case, g is the inside function. So I'm going to find the limit as x goes to 1 of g first. Again, if that limit doesn't exist, then the limit of the whole composite function doesn't exist. So here's g here. So let's find the limit of g as x goes to 1. So here's 1 here. I think it's clear to see that this limit is 3. I think we've done enough limits to understand that this limit is 3. Okay, so now let's see if the outside function f is continuous at 3. So here's x equals 3 here. So let's see if it's continuous. So do you see a whole, removable discontinuity? No. Do you see a jump discontinuity at 3? No. Do you see an infinite discontinuity at 3? No. So it appears it's continuous at x equals 3. So therefore, the value of the limit would just be f of 3. And f of 3 is 0. So our answer is 0. So that's how we do case 1. Case 1 is the most traditional case. That's the case most of us have been doing for years. Case 2 and case 3 are a little more rare, and they're the ones that caused all the hysteria last year. So let's take a look at case 2. All right, so here's case 2. So it reads pretty much the same, except for this statement. F of x is not continuous at x equals L. That's going to be the issue for case 2 and case 3, that the function is not continuous at the limit of the inside function. So again, the limit as x goes to c of g, the inside function is L. So in this case, the outside function, which in this case is f of x, is not continuous at the value of the limit of the inside function. So what do we do? So for this particular case, it says g of x approaches L from the bottom as x approaches c from the left and the right. So g of x approaches L. Remember, L is the limit of g. So we're saying it's approaching that limit from the bottom of L. If that's the case, then the limit of the composite function is going to be the limit as x goes to L minus of f of x. So again, here's the case. First of all, f is not continuous at x equals L. L is the value of the limit of the inside function. If g is approaching L, so if g is approaching its limit from the bottom, from below that value, as x approaches c from the left and the right, then the limit of the composite function is the limit as x goes to L minus of f of x. That still may seem like a lot. When we look at an example, it should clear up a little bit. So let's look at an example of case 2. All right, so here's an example of case 2. So in this particular problem, we're finding the limit as x goes to 1 of g of f. We're finding the limit as x goes to 1 of g of f. So in this case, the inside function is f. Again, first thing I always do is I take the limit of the inside function. So I'm going to take the limit of f as x goes to 1. And this is the graph of f here on the left. This is the graph of g here on the right. So I'm going to take the limit of f, the inside function, as x goes to 1. So here's 1 right here, and it looks like that limit is 2. Hopefully everybody will agree that the limit of f of x as x goes to 1 is 2. So we always take the limit of the inside function first, and then we go to the outside function to see if it's continuous at that point. So we got 2 for our limit. So now let's go to the outside function, which is g, and look at g at 2. And lo and behold, we have a jump discontinuity at 2. So right there, you see a jump discontinuity. So g, the outside function, is not continuous at the value of the limit of the inside function. So then we have to go back and see how the inside function is approaching its limit. You see how this is approaching from below? As I come from the left and the right, it's approaching from below 2. These numbers are coming from below 2. You see how we're coming up to 2, coming up to 2 as we get closer and closer to 1 from the left and the right. We call that approaching the limit from below. So since we're approaching the limit from below on the inside function, we can find the limit of the composite function by finding the limit of this guy as x goes to 2 minus. So below we do minus. So we're going to find the limit of g as x goes to 2 minus. And so that's finding the limit from the left, and that limit obviously is 1. So that limit is 1. So again, in this case, it was approaching this limit from below. Hopefully you can see that these values are coming from below 2. There's no value above 2, so they're coming from below 2 as I get closer and closer to 1. So that's what we mean by approaching the limit from below. So now we'll look at case 3, and case 3 will be concerned with approaching the limit from above. And if what we're saying, how it approaches from below, doesn't make sense, when you see a graph of what it means to approach from above, it'll probably make more sense to you what we mean by below. Okay, so let's look at case 3. All right, so this is case 3. So again, f of x is not continuous at x equals L. Again, L is the value of the limit of the inside function. But in this case, G approaches L from the top, not from below, but from the top, as X approaches C from the left and the right. So in this case, the limit of the composite function is going to be the limit as X goes to L plus of f of X, the outside function. So if it approaches from below, like it was in case 2, we take the limit as X goes to L minus. If it approaches from the top, as it is in case 3, we'll take the limit as X goes to L plus. So let's look at a case 3 example. All right, here's the case 3 example. So this problem, we're finding the limit as X goes to 2 of f of G. The limit as X goes to 2 of f of G. So the first thing I'll do is I'll take the limit of the inside function. So I'll take the limit as X goes to 2 of G. So this is the graph of G here on the right. So the limit as X goes to 2 of G is 1. The limit as X goes to 2 of G is obviously 1. So now I'll look at f of 1, that's the outside function, at the limit of the inside function and seeing if it's continuous or not. And lo and behold, once again, it's not continuous. There's a jump discontinuity there at 1. So now I need to look how that limit was approached for the inside function. And so if you look at as X is approaching 2 from the left and the right, notice it's approaching that limit from the top. These values are above 1. So it's approaching 1 from the top, from above. So hopefully you have a clearer understanding of what it means to approach from below or from top. Let me just go back to the previous problem just to emphasize. Here, this is what it means to approach from below. You see it's coming from below this value that the limit is. As we approach from the left and the right, it's coming from below this value. Here, it's coming from the top or above this value where the limit is. In this case, the limit was 1. It's coming from above. So when that's the case, we'll take the limit of the outside function at this value from the right. So we're going to take the limit. Again, we found the limit of the inside function to be 1, so we'll find the limit of the outside function as X goes to 1 plus or 1 from the right. And that value from the right obviously is 2. So the limit of f of X as X goes to 1 plus, meaning 1 from the right, is 2. Okay, so those are the 3 cases. Hopefully that made sense, but we're going to do some more examples just to bring the point home a little bit better. So let's look at a few examples and see how they look to us. All right, here's the next example. So this one, and you may see there's only one graph there, and this is the graph of f of X. But we're finding the limit as X goes to -2 of f of X. So it is a composite function. It's f of X. So that is a composite function. So we'll do it the same way. It's just that the inside function and the outside function happen to be the same function. Neat, isn't it? All right, so let's look at it. So let's first find the limit of the inside function, which is the limit of f of X as X goes to -2. So here is -2 there. So the limit of f of X goes to -2 is 1. That limit is 1. So now we're going to see if the outside function is continuous at 1. Again, the outside function is the same function. But look at 1, once again, we have this jump discontinuity. So it's not continuous at X equals 1. So therefore, we look at how it's approaching the limit on the inside. So here it is approaching 1. Would you say that's approaching 1 from below or from the top? I think you would agree it's approaching 1 from the top. So therefore, we'll find the limit of 1 from the right. We'll find the limit as X goes to 1 plus. So the limit as X goes to 1 plus obviously is 1. So our answer is 1. And let's take another example. Let's make the understanding increase. Okay, so this is another f of X problem. So here we're finding the limit as X goes to -1 of f of f of x. Okay, so first I'm gonna find the limit of f of x, the inside function, as x goes to -1. So here is -1 here, that limit is 3. It's obvious that limit is 3. So now I'll see if the outside function, which is also f of x, is continuous at x equals 3. And no, it's not. There's a jump discontinuity there at 3. So I'll look at how x is approaching 3 as x goes to -1 from the left and the right. And it looks like it's approaching 3 from below 3. It's approaching 3 from below 3. So therefore, I'll take the limit as x goes to 3 minus. I'll take the limit as x goes to 3 minus. Below is minus, above is plus. So this is below, so we'll take the limit as x goes to 3 minus. That is -2. Okay, next example. So here we're finding the limit as x goes to -2 of f of g. The limit as x goes to -2 of f of g. So the inside function is g. So I'll take the limit of g as x goes to -2. Again, in all these graphs that have two graphs, f is on the left, g is on the right. So let's take the limit as x goes to -2 of g. Here's -2 here, so that limit is -2. That limit is -2. So let's see if the outside function f is continuous at -2. Oh, no, it's not. Jump discontinuity is not continuous at -2. So now let's see how x is approaching, how the limit is approaching -2. So here's -2. Would you say it's approaching below or above? Now look and think for a second. Pause the video if you need a minute to think. Just look and think for a second. So do you think it's approaching this -2 here from above? Or do you think it's approaching this -2 from below? The answer is neither. So from the left, it's approaching it from below. So this is coming from below -2. But on the right, it's coming from the top of -2. It's coming from above -2. So you don't have any unison there. You can't say it's approaching just from above or just from below. So what do we do in that case? Well, in that case, the limit does not exist. So there are three things that have to occur here for the limit to exist. One, the outside function is continuous at the limit of the inside function, the classic example. Two, the outside function is not continuous at the limit of the inside function, but it's approaching the limit of the inside function from below. Or three, again, the outside function is not continuous at the limit of the inside function, but it's approaching the limit of the inside function from above. Those are the three things that are going to give us limits for these composite functions. If the outside function is not continuous at the limit of the inside function and is not approaching wholly from above or wholly from below, the limit doesn't exist. And if the limit of the inside function doesn't exist, the whole limit doesn't exist. Okay, let's do our last example. All right, so this one's the same graph actually, and we're finding the limit as x goes to -2 of g of f. So in this case, f is the inside function. So I'm gonna find the limit as x goes to -2 of f first. So here is f, here is -2. What do you think that limit is? That limit doesn't exist. There's a jump discontinuity. That limit doesn't exist. So if the limit of the inside function doesn't exist, then the whole limit doesn't exist. Okay, so that completes limits of composite functions. Again, this can be a little challenging, so I'm very interested to see how you handle this one. If you have any questions, you know how to reach me. We'll see you next time.